Taking a look at a problem, suppose I have a circular track here, and I have a car that is traveling around this track. Let's make it for right now, let's just assume a flat track. So from a back view, so this is overhead and a back, and the velocity is into the page here because it's from the back point of view of the car. If we did a force diagram here, recognize that what the car, again, wants to do is it naturally wants to go in a straight line. But if you're driving in a circle, there's got to be something pulling you in. In other words, there's a centripetal force. And centripetal force is not some special force. We're not adding to F-tong. So there must be some force holding it into the circle. There's got to be a net force in that direction because that's the direction of the acceleration towards the center of the circle. So if we did a force diagram of this one, that normal force up, weight acting down, and then there's actually friction acting this way because again the car wants to go in a straight line. Something is keeping it from doing that. If this were ice, this thing would go straight forward, but there is friction holding it in, and so this is the centripetal force in this particular case. If we assume that, so we have some static friction, we don't want the car sliding at all, so if we want to figure out what is maximum speed so that it will not slip, well, we have some R there. We can do that. I know that y is y minus w, oops, set our coordinate system, I hat and j hat. So my j hat equation is y minus w is equal to 0. My I hat equation is F is equal to ma in centripetal. Substitution now, so I have y equals mg, and down here I have mu s y equals mv squared over r. And the reason why I can plug in mu sy, if you recall, static friction is less than or equal to mu sy, but I'm looking at an extreme here. I want to figure out what is the maximum speed, and so I'm going to be at that maximum static. And so plug that into here. I have mu s mg equals mv squared over r. The mass cancels out, so the mass of the vehicle is irrelevant as long as it actually exists. And so v becomes the square root of mu s gr. That is the speed, the maximum speed a car can take on the flat surface. I'm trying to remember what mu, between tire, rubber, and asphalt, for some reason I'm thinking it's 0.7. I'd have to look that up again. We can now do a variation of the problem where instead of having a flat track, it is banked, some angle theta. So again, looking at the circular track here, but this time it's at a tilt. It looks like box on ramp type problem, except the acceleration is not down the ramp, the acceleration is towards the center of the circle. This car is traveling in a circle like this, it is not traveling in a circle like that. So when we set up the force diagram looks a lot like box on ramp. So there's my car there, normal force pointing this way, weight pulling, going down, and let's assume it's frictionless. So the coefficient of friction is 0, same with the kinetic coefficient. So when I break it up, I set up my coordinate system, I hat and j hat. This is what I'm breaking up. Unlike box on ramp where I'm breaking weight up, this time I'm breaking normal force up. Now doing a little bit of geometry here. I know normal force is perpendicular to that, to the ramp itself. That angle is theta. This angle right here must be the complement of theta, so I'm going to label that theta prime. When I'm breaking a vector up, so if that's my normal force that I am breaking up, that's the hypotenuse, and I break it up into the part that are basically along the lines of my axes here. So if that's y, this angle right here must be theta. So this is y sine of theta, and this side right here is y cosine of theta. So my force diagram now has been simplified into weight y sine of theta to the left and y cosine theta up. My equations of motion, I have y sine theta is equal to mv squared over r. and y cosine theta is equal to, or minus weight equals 0. So from this, y cosine theta is equal to mg. So given my two equations here, again, that right there is my centripetal acceleration. I went ahead and skipped a step. So I have y sine theta divided by y cosine theta equals mv squared over r divided by mg. Basically, I'm dividing the left-hand sides and the right-hand sides. My normal force cancels out, which is fortunate. Mass cancels out, which is expected. Tangent of theta is equal to v squared over gr. So my speed is the square root of gr tan theta. So what's happening here is that as this car is traveling around this curve, if this ramp is frictionless, that if the car goes that speed, then it will just very nicely go cruising around and not slide up or down the track. Now we can make it more complicated by adding friction, and there will be videos posted from class where I actually go through that. So let's actually do some numbers here, just give some idea of speed. And so if r is 100 meters, this is the radius of curvature of the track, that number right there. Let's assume it takes place on Earth, so 9.8 meters per second squared, acceleration due to gravity. And let's make that angle, say 30 degrees. Then, let's make it 20 degrees, make it a little bit flatter. And so the maximum, or the ideal speed to basically cruise around this curve without sliding up or down the track is going to be the square root of 980, that's gr, times the tangent of 20 degrees, which is 18.886 meters per second. So travel faster than that, you'll start to slide towards the top of the ramp. Travel slower than that, you'll start to slide to the bottom of that. And so now, if we throw friction into the problem, so have friction between the tire and the road, tires and the road, then if he's traveling at 20 meters per second, he wants to slide towards the top because he's going over that ideal speed, which means the friction is acting down the ramp. If he's traveling under this speed, then he wants to slide down the ramp, and so friction will be acting up the ramp on him. And so that's why defining this critical speed here is important when we bring friction into it. And all of that, again, is discussed. Oop. The part that was left off. So there's the speed, the square root of gr tan theta, as used up here.